What we're looking at now are the acidic and basic properties of salts. And a salt is an ionic compound. And if we remember, ionic compounds are made up of cations, which have a positive charge, usually a metal, and anions are ions that have a negative charge. Now, we've already looked at the acidic and basic properties of some ions. For example, these anions here are all conjugate bases of a weak acid, so they have a Kb. So if I had a salt that had an anion that was the conjugate base of a weak acid, it would affect the pH of that solution. If it has a Kb, it would react as a base, and it would increase the concentration of hydroxide. Likewise, we've already seen that ammonium, the conjugate acid of ammonia, has a Ka. So if ammonium was the cation in a salt and it dissolved, it would increase the concentration of hydronium and therefore make the solution more acidic. So let's look at anions first. Anions are bases, and as such they react in this hydrolysis reaction in the typical way that bases react with water when they dissolve in water. This anion is going to accept a proton from water. That's the Bronsted-Lowry definition of a base. And then it's going to form the conjugate acid and hydroxide. And so by forming more hydroxide in solution, it affects the pH and also fulfills the definition of a base for the Arrhenius definition. Now let's look at the reaction of cations. We've already seen that if a cation is the conjugate acid of a weak base, such as ammonium, then it will increase the concentration of hydronium and thus lower the pH. However, we haven't looked at how a metal cation can change the pH of a solution. If a metal cation is dissolved in water, it can affect the pH due to its interaction with water. We want to remember that water is a very polar molecule, and this oxygen is electron-rich and very electronegative. So the attraction between non-bonding electrons on oxygen and the metal causes a shift of the electron density in the water, meaning these electrons are really going to be attracted to this positive charge, and so there's going to be a shift here. If we have a greater charge on the cation and a smaller size, then that's going to make the cation more acidic. So for example, iron plus 3 would be more acidic than iron plus 2 because iron plus 3 is smaller and has a greater charge. So this attraction here will cause more of the electrons to be attracted to this positive charge, and that can make the water acidic. So I drew this picture here that I think does a better job of describing what's happening. So most metal cations have 6 waters around them, and that's just due to the geometry. Most metal cations are within a relatively small range of diameter, and the water molecule has a very specific size. So this is a two-dimensional rendition. There are 4 water molecules drawn in this plane, and if this was a piece of paper, there'd be a water molecule above the plane of the paper and a water molecule below the plane of the paper for a total of 6. So here these electron pairs are attracted to this positively charged metal cation. And if this charge is great enough, it can actually accept an electron pair from the water molecule. And when it accepts that electron pair from the water molecule, what happens is a proton gets clipped off. So we can imagine this partial negative here and this partial positive here, causing a polarity between this bond. And if this attraction is strong enough, it can actually take the 2 electrons that are in this bond holding this proton to this oxygen and accept it to make this bond. So then the proton is removed from the water and is floating around in water. It will be accepted by a water molecule to form hydronium, but that's how metal cations make a solution acidic. So if we were to look at the balanced chemical equation for this reaction, here's our metal cation with 6 waters around it, and it has some particular charge. Then what happens if that charge, this is an equilibrium here. If that positive charge is strong enough to attract 2 electrons from the water molecule to make a bond. Basically what happens is we have a reaction or a bond between metal with this +1 charge and hydroxide. And hydroxide. So the metal originally had a certain charge, but when it forms this bond with hydroxide, its charge decreases by 1. So that's why we have N-1 over here is the charge of this whole species. And then we have H+, and if we were to look at the overall charge on the left-hand side and the overall charge on the right-hand side, they would be equal to one another. And then this proton here is going to react with the water to form hydronium. So this whole process shows how the dissolving of a metal cation increases the acidity of a solution, or in other words, decreases the pH. So looking at what happens in terms of the water molecule that reacts with the metal cation donates a pair of electrons as a bond, and it basically forms a hydroxide and a proton. This gets clipped off here. These 2 electrons stay with the oxygen, the 2 electrons that were being shared. And this proton here has no electrons. So that's basically how water gets split by a metal cation. Now, one thing that we have not talked about yet is the anion that is the conjugate base of a strong acid, or the cation that is the conjugate acid of a strong base. The anion that is the conjugate base of a strong acid will not affect the pH. So it is super important, sorry about that. It's super important that we know what our strong acids and our strong bases are. And these are found in table 4.2, page 125 of the textbook. So if we look at the conjugate bases, chloride, bromide, iodide, chlorate, perchlorate, nitrate, all of these will not affect the pH. Now, sulfuric acid, sulfate actually does affect the pH. We may pretend that it doesn't, but it actually does. But any anion that is the conjugate base of a weak acid will increase the pH, meaning it will make the solution more basic. So here are some common conjugate bases. All of these, from fluoride down to carbonate, would make a solution more basic. The cation, that is the conjugate acid of a weak base, will decrease the pH, meaning it will become more acidic. So ammonium, for example, will make the solution more acidic. And the cations, or conjugate acids, of a strong Arrhenius base will not affect the pH. So here we have our strong bases. So lithium, sodium, potassium, rubidium, cesium, barium, strontium, calcium, all of those we consider not to affect the pH. And then other metal ions will cause a decrease in pH, meaning making them more acidic. Now, when a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, we have to look at the Ka value of our conjugate acid and the Kb value of our conjugate base. Whichever value is larger will determine whether the solution will be acidic or basic. So let's just take a quick look at this little example here. We have some solutions here, and these all have an indicator in them that will change color as the pH changes. Here I have sodium nitrate. Sodium is the conjugate acid of sodium hydroxide, so it will not affect the pH, and nitrate is the conjugate base of a strong acid, so it will not affect the pH. So this has a pH of 7, which is what we expected. Calcium nitrate. Calcium is the conjugate acid of a strong base. Nitrate, the conjugate base of a strong acid, so the pH is about what we expected. Now here we have zinc nitrate and aluminum nitrate. Nitrite, we've already established, does not affect the pH, but zinc and aluminum, as cations that are not conjugate acids of strong bases, will affect the pH. Zinc has a charge of +2, aluminum has a charge of +3, and we can see that aluminum is clearly much more acidic than zinc, and that's what we would expect. It has a smaller size and larger charge.